Welcome to the 28th and the last class meeting of the Introduction to DSP. I decided not to assign the homework, so happy. We will have the exam on, I believe, Wednesday, right? Is it Wednesday? Is it Wednesday? Yeah. Wednesday 7 in this class meeting room. For the voluntary project, you have to be approved the topic before you take the exam, so you have less than a week. Okay, here goes the overview. We've covered around half of the topics, and currently just covered the chapter 10 on the analysis of signals using DFT. And today, I'm going to talk about some details on chapter 10, and we'll move to chapter 11. I've decided not to cover these three and some of other chapters because we don't have enough time. It seems that this is the first semester to teach DSP, and I've spent too much time reviewing the signals and systems part of the discrete time signal processing. Probably next time I have to skip that, asking students to view the lecture videos of this year. Anyway, here goes the review. In the last class meeting, we studied the time-dependent Fourier transform, and that was designed to overcome the problem of DTFT. So DTFT of a signal X was defined as what? X of n times e to the negative j omega n for all n. And here, time-dependent DTFT, simply time-dependent Fourier transform, is a little bit different. We have two parameters, n and lambda, and the summation is over m, and we have the signal x of m advanced by m and properly windowed, and discrete time Fourier transform is performed. So can you see the similarity and difference of these two? So the time-dependent Fourier transform can be understood as what? As a variable of m. This signal, this product signal, is discrete time Fourier transformed, where parameter is, lambda, not omega. Okay. And so this lambda corresponds to omega here. Okay. So lambda and omega are radians per second. And n is the amount of time advance. Got it? So the question is, what is the domain of this function and the range of this function? This function x here is from R into C. Omega is the variable, and it can be any real number. Of course, this DTFT is periodic, so what you need is just one single period of length 2 pi. However, anyway, x is basically a real valued function. And what about this x? Even though we use the same name, you know that the upper one is a single variable function and the latter one is a 2 variable function. Here, n is an integer, and we have a Cartesian product of the set of integer and the real number. And again, the range is the complex number. Got it? So time-dependent Fourier transform is a special case of discrete time Fourier transform. But since we have a window function and some proper time advance, we have two parameters. Now, this DTFT can be sampled because for lambda, we have uncountably infinite choices. So, and again, if W of M is of finite duration, then we may apply not the DTFT, but the DFT to evaluate this function at some discrete points. So, for example, this is of length L, and we take V of M as what? The product of these two. And we pad some zeros and then perform DFT with endpoint DFT. Then we get capital N minus 1 complex values, which corresponds to what? Which corresponds to X of N. And what about this lambda? Lambda is 2 pi K over N. Got it? So under certain conditions, like rectangular window of length L, and we pad zeros, so we have n-point DFT. So this is the case entry of the n DFT output. Then what? This is same as, just a second, need n. So superscript or subscript. Let me use something like this. Okay. Then we have equality like this. Now, n is n ranges and yeah, n ranges from some number. This is what you are going to choose, and k ranges from 0 to n minus 1, so that you can plot this one. Now, this is a complex valued one. Sometimes we take the magnitude or magnitude square of it. And moreover, we take 20 log of the magnitude square. In that case, we call the output spectrogram. Got it? So DTFT is a transform. Short-time Fourier transform is kind of discrete sampling of DTFT, and 20 log 10 base magnitude square of short-time Fourier transform is called the spectrogram. Got it? Then we move to section 10.3 and 10.4. The most confusing part of this one is that actually we have a bigger picture. So this is the topic of chapter 11, and these are the topics of section 10.3 and 4. How can you group this? Because in many engineering problems like radar signal processing, we need to estimate power spectral density of stationary or sometimes non-stationary random processes. By the way, I've found that the Department of Electrical Engineering offers next semester the spectrum estimation course as a graduate course. So if you have interest, then take it. Got it? You will see a lot of periodogram averaging, and also other topics I'm just scratched today. Got it? So at this point, just believe that the estimation of a power spectral density is a very important topic. And there are basically two big approaches. One is so-called parametric approach, which is the topic of today. And in the sections 10.3 and 4, we studied non-parametric approaches. And these non-parametric approaches are both based on the definition of power spectral density. The first one is more related to the definition itself, and the second one is related to the so-called Wiener-Khinchin theorem. So according to the Wiener-Khinchin theorem, instead of directly compute the power spectral density, what you need to do is first estimate the autocorrelation function of a random process and then perform Fourier transform. So in section 10.3, we've seen how to, what is the definition of periodogram and why periodogram gives us some estimate of the PSD. And in section 10.4, it was just mentioned that, hey, you estimate the autocorrelation or autocovariance function and then Fourier transform it to estimate the power spectrum. And while we were studying this one, I've talked to you how to estimate the continuous time random processes power spectral density by using what we learned in this course. But at that time, I didn't carefully detail all the coefficients you need. So here I have some kind of brief summary. So be careful. Suppose we have x sub c of t, which is a band-limited random process, but possibly complex valued, or if you want real valued. And we assume that the bandwidth of this random process is b in complex baseband. So 2b is now chosen as a number that is less than or equal to our sampling rate. So it's like this. So here we have a continuous time random process whose power spectral density is to be estimated. But since we cannot do that, we approximately estimate by sampling and doing some discrete time signal processing. So here comes the sampling rate. Got it? So we have a continuous time random process. Here goes to C to D conversion. And then here we estimate PSD of the continuous time random process. Got it? So here in the first part, we convert this one into continuous time to discrete time, just assuming the signal is band limited and assuming our sampling rate is greater than or equal to the Nyquist rate. Got it? So conversion is done very simply. And here, even though this is usually a power signal, so we don't have continuous time Fourier transform, just temporarily believe that we have some CTFT existing for this one. Then what we learned in this course says that the discrete time Fourier transform of the sampled signal. So here goes x of n. X of n has the DTFT. This is DTFT. And if we evaluate at omega equals 2 pi f, then this DTFT equals what? Sampling rate times the folded spectrum, properly normalized. Or if you want, you can change this one to FT, and then what you have, this one. Got it? Probably this would be more appealing because you just shift the original spectrum of a continuous time signal by integer multiples of sampling rate. So here goes the sampling. Now, we want to know about this one, right? So for f less than or equal to, the absolute value less than or equal to 1 over 2ts, we may say these are true. We just multiply ts to both sides to get this one. Got it? Now, we've just seen in the last class meeting that suppose our sampled signal, already sampled discrete time signal, rectangular window of length, this is 2n, probably something like this. Anyway, and if this signal, this is again discrete time signal, discrete time Fourier transformed, then we have what? The DTFT evaluated at k over n is simply the case DFT output of the vector v with length n, right? Of course, you can choose this as L and may pad zeros to make it of length L, length n. Okay, it is okay to choose any one. But anyway, so now what we are going to do is to combine these two. And here, the combination requires our definition of the power spectral density of the continuous time random process, which is the limit of the what? Expectation of the energy spectral density. And this energy spectral density is what? Is kind of here, okay? Even though they are not the same, right? So, because this is time limited with delta, so just assume that this holds, okay? Got it? Then what we do is that we just drop this one. We cannot take the limit, so this is gone. But what we do is that we assume that we observe M independent or uncorrelated realizations, and this superscript is the index of each realization. Then we observe the zeroth realization, and we sample, truncate, and Fourier transform it. Of course, discrete Fourier transform it, and we get this one. So this one is here, and that is what? Ts times DTFT. So here, if we define V, then it's V of M, V superscript M evaluated at e to the j 2 pi FTS. Now, if you choose discrete points because we performed DFT, then we eventually have this relation. Got it? See that here we have Ts squared and here Ts. So we have Ts and N here. N is the number of DFT points. Got it? And what is Vk? Vk is the case coefficient for the mth observation. So for each k, you average m of them. Got it? By doing this, you can estimate a continuous time signal's random power spectral density. Now, why the question would be why we need this? And there are some cases. Suppose that you have a nonlinear power amplifier that amplifies the transmitted signal. And here goes your, for example, OFDM modulator. The problem is this one. At this point, without any nonlinearity or nonlinear distortion, you can estimate the PSD of the continuous time signal, continuous time random process modeling an OFDM signal mathematically exactly. You can do that. So power spectral density can be written as a formula written without any nonlinear distortion, nonlinear mapping. However, what is important is the power spectral density at the output of the power amplifier, because that is the signal really transmitted. And if a regulatory organization examines your transmitter's integrity, what they do is that they disconnect your transmit antenna and connect their spectrum analyzer to see what is wrong or not. Now, there are many ways to mathematically model a power amplifier. Of course, it's not impossible to exactly model using some simple model. By the way, this power amplifier modeling turns out to be a huge area of research in microwave engineering. So as a communication engineer, I just thought that, hey, there should be just only a few simple models, possibly nonlinear, so I can do something. And I started the research ambitiously, and there was some door while I was searching for such and such papers, and suddenly when I opened the door, there was a big universe there. So what I'm saying is that this single nonlinear device, the power amplifier, is very hard to exactly model, which means that there are many different models. All of them are not exact, but having a different level of accuracy and complexity traded off. So in some sense, some sophisticated model can give you at least the distorted version of X of t very accurately. So here goes the distorted version. And we assume that we have some formula here to map X sub c of t to X sub c tilde of t. The problem is, what is the power spectral density here? We cannot have some exact formula. In that case, the simplest thing is what? To rely on this approach. Got it? So what we do is that we sample this one, and of course you can use spectrum analyzer, but what I'm saying is that by numerical simulation, okay? So what we do is that we sample mathematically X tilde sub c of t, and then what do? We apply rectangular window, perform DFT, and new segment comes in, sample, apply rectangular window, perform DFT many times. And when you average all of them, you need to first take the magnitude scale of each vector, but you need to properly scale them so that you have no problem in the out-of-band emission, less than some dBm, blah, blah, blah. Got it? So this scale is very simple here, but needs complete understanding of what's going on when you sample a continuous time signal and compare the CTFT and DTFT. And also, it requires the knowledge on how to sample the DTFT by using DFT. Got it? Anyway, so that's all for chapter 10, and here goes chapter 11. So the topic of chapter 11 is, as the title says, parametric signal modeling. And this is, at the first glance, strange, sounds strange. But let's see. So here, in the introduction of the textbook, the authors review what we've studied so far. So here is the mother course, Signals and Systems. And here is the discourse, Introduction to Discrete Time Signal Processing. And we have discrete time signals and systems. And the question is, what have we done to analyze or represent a discrete time signal? And the authors say that the first one is to use the shifting property. Second one is Fourier base representation. What does that mean? Suppose you have a discrete time signal. Then this first shifting property-based representation means you view x of n as what? The delayed and scaled versions, some of the delayed scaled versions of delta functions. Got it? So x of n is a scaled version of delayed delta functions summed up for all m, right? And this was very important because using this one, here we could define the notion of what? Impulse response of a linear system. By the way, we had two impulse responses. One is for linear time varying systems impulse response, and the other was for linear time invariant systems impulse response. And using the property of the impulse response, we could do a lot of things. What? For example, given two LTI systems using the commutativity, associativity, and distributivity of the convolution sum, we could eventually, for example, show that serially connected to LTI systems, their order could be switched without affecting the output, something like that. So, and also about the causality, the LTI system causal means its impulse response is a causal signal. The LTI system is bistable if and only if impulse response is absolutely summable. In that sense, this representation, shifting property based representation of a discrete time signal had many interesting results. And another thing was what? Another thing was the Fourier basis approach. And the synthesis equation says that our discrete time signal can be viewed as uncountably infinite sum of scaled complex sinusoidal signals. So here, as a function of n, right? Function of n, if we change radiant frequency omega, we have different signals. As far as omega and omega prime has same modulo 2 pi, different modulo 2 pi values. Got it? So, by the way, this representation was motivated by the fact that if we have discrete time LTI system, so actually this is also motivated by the result of this representation. So if we have LTI system, what was good? Every LTI system has what? This e to the j omega n as an eigenfunction. So that motivated our new representation. And from this one, of course, this is, it can be said that the inverse discrete time Fourier transform. So we have the so-called frequency domain analysis, and even the design of LTI systems. By the way, some student asked me long ago, according to our high school knowledge, what is the definition of frequency? And why we have negative frequency here, right? So question is, what's the meaning of negative frequency? Your high school definition of frequency is defined as inverse of period of some signal, periodic signal. That definition still is okay. However, in our DSP, frequency, when we say, means what? What is the value of omega in our Fourier basis? Okay? So in Fourier basis, e to the some positive j omega 0 n is different from, in general, e to the negative j omega 0 n. They are, in general, different signals. Got it? But if you just view the period of these two signals, and according to your definition or high school definition of frequency, then they have the same frequency and there is no negative frequency. But when we talk about negative frequency, we assume we are using Fourier basis, and in Fourier basis, we have negative frequency in general different from positive frequency. So you should be able to answer such a question by, for example, your friend in some other department who never had a chance to get out of high school definition of frequency. Got it? Anyway, so our second representation gave us the chance to develop frequency domain approaches to analyze and design systems and signals. And that was almost every part of undergraduate signals and systems and digital signal processing course. And in the graduate level, discrete time signal processing, and if there is continuous time signal processing, there are more. For example, as I told you, there would be spectral estimation course in our graduate electrical engineering department in the next semester. And there we talk other than these two representations. And one of them is what we are going to see. And here the author says that even though these two are very important methods of representing a discrete time signal, or possibly you have counterpart in continuous time, we have something more. And there are many more representation methods. For example, suppose you are more interested in the discrete signal processing, not discrete time, which means that vector signal processing, then probably you can do what? You can rely on linear algebra. Because our system would be written this way, right? Input signal is a vector, output signal is a vector. We have a linear mapping, means there exists a matrix m by n that makes y equals hx correct. And you can find a lot of analogies between discrete time signal processing and this linear algebra. For example, if matrix H is so-called a Toeplitz matrix, then it could be some finite samples taken at the input and output over discrete time linear time invariant system. And if H is a circulant matrix, then you have some other property, blah, 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 blah. So even though in your undergraduate course of applied linear algebra, your professor in math department probably had never linked your topic with signal gen systems, you must do it yourself. Because now you have studied signal gen systems, you have studied applied linear algebra, and you have studied digital signal processing. And unfortunately, since this course does not require linear algebra, I'm not going to put many problems asking you to link the linear algebra with this course. But anyway, so here, if the matrix is circulant, then you can use DFT. Inverse. So what you do is that you apply DFT matrix to both sides, and you insert DFT matrix times its inverse between H and X. Then what happens? You can group these three matrices. Oh, sorry, something's wrong here. Okay. So what is this one? This vector y tilde is the DFT of y, and this x tilde is DFT of x, and this h tilde is what? Kind of similarity transformed version of h. And if h is circulant, then you have a diagonal matrix here. Something like that. So again, in linear algebra, Fourier basis for this discrete Fourier transform is very, very important. However, in some graduate courses, you study completely different bases. For example, you may use Hadamard matrices to transform your vector. And this Hadamard basis is often used in image processing and transmission of images. And there could be a lot of other bases. So you have just seen a very small part of a big picture. So let's suppose this is the set of all useful bases for signal representation. And here goes what? Shifting property based, which means that the direct delta basis and this is Fourier basis. And this is Hadamard. And a lot others. Got it? You've just seen this and that. Got it? So never forget that what you've learned is a part of this big set. However, many important lessons you've acquired studying these two extends or directly applied to study these other basis-based representations. So you should be able to study yourself about other cases. Got it? Anyway, so these are kind of group set of all useful bases for signal representation. The problem is that what we are going to see in chapter 11 is not this one, not in this set. Probably we have to consider a bigger set, and here is what we are going to study today. Got it? So I hope, even though I just scratched the surface of this big set, I hope you can distinguish the difference between this group of signal representation and that group of signal representation. They are very different. Here, let me emphasize, you choose your basis, then rewrite your signal as a weighted sum of basis functions. But here it's a little bit different. And at the first glance, it's very, very weird. But interestingly, this one, so-called parametric signal modeling, is very closely related to what we are doing currently for AI/ML modeling. Interestingly, here comes the same terminology, model. See that? Before, when we study the signal representations, we wanted to rewrite x of n as a weighted sum of basis functions, right? But here, it says parametric signal modeling means that we have a model for a signal. What does that mean? When we talk about a model or modeling, it's closely related to the term simplification. Of course, with a small number of parameters. Got it? Now, here goes an example. Suppose you have a continuous signal, very smooth, we assume, defined on a finite interval, real valued function defined on an interval. Here goes the graph, A and B, and you have some function, so-called G, okay? Now, G could be any continuous function on this interval. In that case, how many parameters we need to completely specify this function? How many? In general, uncountably infinite. Because this graph itself looks simple, but it could be any function. And a function means what? Given an input, you have a corresponding output. So you have a pair of two numbers. One is from the domain and the other is from the range. And since this is a real valued function, you have uncountably infinite parameter pairs you need to describe. Got it? Now, here goes an idea. Suppose we model this function as a polynomial. Got it? Now you got it. Polynomial means what? Polynomial means you have the maximum ordered term and other terms like this. Got it? So if you model this function as an mth order polynomial, what does that mean? You sacrifice the accuracy of approximating this g of x, but you have it, as you see here, what? Finite number of parameters. Capital M. Got it? Now, this is the original signal, and your G tilde is what? Is a model. So this block is the mapping rule G. And you have another block that has inside mth order polynomial, and you have g of x. Got it? And this is what? This is function approximation. Very important topic in AI ML modeling, actually. In many cases, what we do have around 1/3 of what we do in AI ML, we learn the parameters to model this function g by using our some simplified small parameter sized system. Of course, these days, this small parameter could be million, but million is much always smaller than uncountably infinite number. Got it? Anyway, we are doing almost the same thing in this parametric signal modeling. So suppose S is the signal you want to rewrite, represent. Okay, so you have S, that is the starting point. You have signal S. Now, you want to, now discrete time signal still has countably infinite parameters for general S of n, right? Because n could be any integer, right? And even if you truncate them, still you may have very large number. What we want is that we rewrite somehow this S of n with small number of parameters. And here goes the idea like this. What we are going to do is that instead of signal S, we want to approximate S with S hat. Now S hat is what? The output of an LTI system to an input. So it's like S of n is given, and you want to find Vn and H of n. And it looks very strange that this equation has infinitely many solutions. So how can you find this one, right? And there goes some constraint like mth order polynomial thing. So what we do is that, as we learned in this course, not every discrete time system, but the discrete time systems that can be represented or that can be well approximated by a linear constant coefficient difference equation, then we have what? We have its Z transform given by a rational function of Z or Z inverse. So we restrict this one as a rational function of Z or Z inverse. Got it? And rational function means that numerator has finite order and denominator has finite order, exactly as we've seen here. By the way, given our original high school-like problem of approximating a continuous signal on a finite interval, actually, this is motivated, this model with polynomial modeling the function is motivated by motivated by, I just forgot the name, just a second. I forgot. Yeah, I forgot totally the name. Okay, anyway, there is a, yeah, just a second. Let me remember. I cannot remember. Anyway, so this is very straightforward, motivated by a theorem. And actually, there is another approach where I put the link of some YouTube video in our playlist. And you see that this rational function approximation is not limited to our digital signal processing. It has been done. Its history is as long as this method. Got it? So ratio of polynomials to approximate a function has been a tradition in simple approximation and so-called modeling of a function. The trouble is this one. We are not doing just modeling a given function. In our problem, we are given S, and we want to find V and H. Even though we limit the numerator and denominator orders, still there are too many possibilities of choosing input signal and this one. The simplest approach would be just, hey, let's simplify V of n, the input, as delta of n, right? Then this is same as that one, or this is now approximated as a what? A discrete time signal whose z transform is a rational function. That would be a way, but still that's not the general practice. Interestingly, as I told you in the last class meeting, in speech compression, people have found that speech signal can be well modeled as what? As some signal input, especially this vocal cords, periodic generation of impulses with some so-called all-pole model. Means that now h of z here, our numerator is replaced by some constant. I remember k they used. Okay. And then here, what we need to specify is the order of the pole and need to find AKs and this constant capital K. But you may say that, hey, still I don't know how to determine the input V. Got it? And input V, especially, as I told you in speech compression, especially for vowels, not consonants, a periodic signal, that is given by this idea. Okay, G is used. Okay, let me use G here. So suppose we have found some model of S as a convolution of V and H. Then we have something like this, right? Now suppose we find the inverse function of this one, assuming inverse exists. Okay? And one good thing for all-pole system is that if we take the reciprocal of the system function, we have the G transform, the system function of the inverse system. So the idea is like this. Here goes S. Here goes S. And if we have inverse function, then we have V, and here goes H, and we have S. If the approximation is perfect, then we have S in and S out. The idea here is to take this one and limit the versatility of this function as what? Hey, we want to model this one as all-pole system, means that this is all-zero system. Okay? Something like that. Then, due to the limitation of its capability, when we try to approximate, we may have some error. That is the idea of this system. So it's like this. So here goes the signal S, and here goes the inverse system, which is now a moving average. And the outputs are subtracted, then usually we call it an error signal. And what we are going to do is that we want to find coefficients of this moving average system that minimizes this error. Got it? That is one choice from many possible choices in finding this system. Got it? So what we are going to do is that we want to find inverse system and this system that minimizes the error signal's energy when we limit the capability of this filter to some piece order all-pole system. Let me repeat it again. Ideally, this is just the inverse of that one. So still, there could be many different choices of V and H, right? Theoretically. Now, what we do is that we limit this one to, in some cases, like speech compression, all-pole system. Then this becomes all-zero system. And now, what we are going to do is that when S goes in, the signal goes in, so we are here, and inverse system tries to regenerate the signal S. Got it? So this tries to regenerate signal S. So this difference, the error signal E of n, is its energy is minimized, then we will be satisfied with our choice of H of Z. So this is one of the methods to choose H of Z. Got it? And let's see the meaning of this one using this formula. So here goes SOS hat, and your output is the moving average of the previous samples. So it's like you want to predict the next value of S, but it has some limitation. So that error is handled by the signal V. But you want to make this energy of the difference as small as possible. So here goes the energy of the error signal, and you want to minimize the energy of the error signal. And fortunately, in many cases, not every time, in many cases, you can formulate this matrix vector multiplication to find your coefficients. Furthermore, in some cases, not always, under the assumption of stationarity of your signal as a realization of random process, this so-called normal equation can be one step further simplified like this, where you have symmetrical matrix. And in this case, they have found an algorithm to recursively find these coefficients. And that is so-called Levinson-Durbin algorithm. Okay, so this is your worker equation, and this is general normal equation. Got it? By the way, this Euroker equation can be found in many, many cases of adaptive signal processing. So whenever you want to develop some recursive algorithm, your basis model would be your Walker equation and Levinson-Durbin algorithm to solve this equation. By the way, so here goes the model again. So again, let me tell you. So H of Z can be chosen as an all-pole system, all-zero system, or general rational transfer function. However, people have found that all-pole model gives us very good solution method. This sounds very similar to a lot of AI ML models. People, for example, wanted to model some inference system using small number of parameters. So it's like random vector observation in, and you want to make an estimator or detector that is translated as a linear regression or classification for AI ML models. And people have developed, for example, Boltzmann machine, and which got the Nobel Prize last year. The problem is that Boltzmann machine has very small capability to model arbitrary distribution, even if it's discrete, random vector. So people started from that and has given Nobel Prize. Now we are not using that. We usually use these days what? Feed-forward neural net based system, so-called deep neural network. Here deep means this is width and that is deep. So we have small number of layers, but each layer has many, many, many neurons with a fine transform, nonlinear mapping, a fine transform, nonlinear mapping, and output, something like that. And if we increase the neurons, which means that if we increase the size of each matrix in our affine transformation, we have to find out much more number of coefficients. However, people have found an efficient way, even though it takes a lot of computation, efficient way to find out those coefficients. So it's like this. Some model, even though it's simple, hard to find the parameters. And some model apparently looks complicated, but there is an efficient way to find the coefficient, and we explore the system's capability. Almost the same thing happened in the history of this signal modeling. People examined moving average model, all-pole model, some other models, and among them, the easiest way is to model the system as all-pole system. And given the all-pole assumption, people develop this idea. Hey, okay, so suppose that past samples of a signal can predict the future value. And it's very natural, right? Of course, there would be some error. Then this error signal is to be minimized to find out the coefficient of the system. An interesting thing is this one. In speech signal, as you have seen, let's say that the 2 plus something equals blah, blah, blah. And here when the person pronounces 2, we have a vowel here, right? And when we make a sound of vowel, we use our vocal code. And at that time, our head and tongue and nasal cavity, all together named vocal tract, can be modeled as an LTI system, especially an all-pole system. So this is modeled as an all-pole system. And here goes signal S of n. And interestingly, if we just apply this idea and find out the error signal, then not the error signal, the V of n, then V of n looks like the impulse train. And this is because like this. This impulse, each impulse generated by our vocal cord actually excites our LTI system to have some transition. And then next impulse again excites, and that kind of periodic excitation of our all-pole system generates some, in a short period, a periodic signal like a signal. And as you've seen in the previous figure, when the short time Fourier transform or spectrogram is shown, you see something very stationary in a short period. What does that mean? Periodic, or almost periodic signal you observe. So people have found a good application of this approach in voice compression and has been used for a long time. Especially when you use 3G, there is a vocoder. And the vocoder is named as self. And the reason is this LP means linear prediction. Because this is moving average system, we have linear prediction part in our model. And what is this C and E? This is cold and this is excited. So if you look at the vocoders, many of the vocoders are linear prediction based SELP, cold excited linear prediction model. And especially if you see very old documents, there is QSELP, and actually QSELP is Qualcomm's cold excited linear prediction method to compress the speech sound. And this QSELP was inside the chip of Korean's first cellular phones. And still, if you are not using high quality speech for your conversation, then still that is used. And especially when you use real home phone, not the internet-based cell phone, then QSEP is applied in some point, especially when you have a long distance communication. Anyway, so I talked about some interesting topic of signal representation. And here goes one section about model order. And as you've seen, when we choose all-pole model, still we have a freedom to choose the order of the all-pole system. And this choice is very similar to hyperparameter selection in AI ML modeling. What is the width and what is the depth of your system, something like that. Same thing. Of course, if you increase the model order, you may have better and better the accurate system. The problem is that we have the problem of what? Overfitting. Sometimes we have too much overfitting if we increase P. So in some cases, we limit our order. One good thing for the all-pole model applied to the speech compression was that since linear prediction was not perfect, we didn't have overfitting problem, but had this beautiful curve like this. You increase the model order, and your error, you may just say error, but it's saturates, which means that you can just cut at some point of saturation, and that is a very good choice of order. So, as I told you in the last class meeting, some brilliant minds in AT&T Bell Labs and some other institutes worldwide, they tried to find out what was the good choice of the order of all-pole system in their code-excited linear prediction vocoder. They spend the entire their life. One interesting thing is this. When I was at your age and just became a graduate student, I thought that time is gone. Now is the time of research where analytic skill and our cleverness solves everything. Unfortunately, after quarter century, the same period has come. And I'm very sorry to see that a lot of brilliant minds like you just go to the graduate school or research institute and contributing by spending your time to find the optimal number of parameters, like reporting your professor and boss saying that, hey, professor, I tried this one and didn't work. So I tried that one and it worked. I'm not sure why it works, but it works. And that time has come again. And I'm very unhappy, actually. But anyway, that's the way of current research. It could be applied to the all-pole model for spectrum analysis. So you will see, definitely, I guarantee that you will see this all-pole model approach again in the graduate spectrum estimation or analysis course. And also a lot of autocorrelation related stuff. Lattice filters, well, I'm not going to cover it. So here goes the last chapters. Chapter 5 is completely omitted. And that was about this part. And chapter 8 was also omitted. Sorry, chapter 6 was also omitted. It's about the structure. And here goes the lattice filter structure of an LTI system and some other directive forms. And also, chapter 7 is skipped, where you design filters assuming that your system has Z transform that is a rational function of Z. By the way, the emphasis on these 3 chapters, I believe, are now significantly reduced, especially for many engineers. Because of what? Because of the tools, very strong, powerful tools to design digital filters. These days, we have the commercial tools to solve almost every problem here. And what you need to do is to be equipped with terminologies related to the filter design, like what is stop band, what is pass band, something like that. And what is the location of pole and zero, something like that, which you learned throughout this course. So as I already told you in the beginning, before the lecture is recorded, I'm sorry about that. I couldn't cover most of the topics in these 3 chapters. So almost only 2/3 or approximately 2/3 of the textbook is covered. And that is my mistake. I spent too much time on the first part, the review part of the textbook. Okay, anyway, so I hope you enjoyed this course, and many of you volunteer to do your project, and also you have good luck in the final exam. Okay, that's all for today.